Hi everyone, welcome back to Math 256. This is Scott. Let's get started. What we're going to be talking about today are three sections, 7.3, 7.4, and 7.5, that will give us several new tricks for either finding Laplace transform or undoing it and finding the inverse Laplace transform. So the first section has to do with a certain trick. It involves translations and partial fractions. So with translations, in other words, horizontal shifts, here's the idea. When we're talking about the function versus the Laplace transform of the function, if we were to multiply by e to the at, that's the same as shifting to the right a units. So in other words, the Laplace transform of e to the at f of t equals f, capital F, of s minus a. Conversely, the Laplace inverse, so the inverse Laplace transformation of a shifted function can then be related back to the unshifted version by adding a factor of e to the at. Now the main tricks for using this, so how to use this. The main tricks for using this all involve trying to rewrite the expression that's given. So we'll use this to find the inverse Laplace. That's going to be the main direction we'll see, although we can go the other way as well. So if we want to find the inverse Laplace transform, then we can try to rewrite the given expression as a shifted formula from the table. So let's see example, a kind of typical example for something like this. Let's say that we had f of s is equal to s plus 1 over s minus 1 squared. Alright, well, if we think about what the important thing as far as the table is concerned, this s minus 1 squared in the denominator is very, very relevant. And in particular, if we can just rewrite the top so that it also is based on s minus 1, then that'll be good. So we want to rewrite so that every s is expressed as s minus 1. So here, what we would be talking about is rewriting this, reframing it, so that everything is based on s minus 1. So f of s would be equal to s minus 1 plus 1, so that makes just the s, plus that 1, because that was part of the formula, over s minus 1 squared. So that's, in other words, going to be s minus 1 plus 2 over s minus 1 squared, which we could separate out as s minus 1 over s minus 1 squared plus 2 over s minus 1 squared. And that's going to be then 1 over s minus 1 plus 2 over s minus 1 squared. And for both of these, we can now either just directly use the table or treat these as shifted versions of things on the table. So then right here, what we would have is so f of t is equal to. So for this one, we're gonna have just e to the 1t. And then here, we're going to have plus, and then this is going to be 2 times t e to the t. And the reasoning on that was that the Laplace transform of t e to the t is equal to 1 over s minus 1 squared. It's a shift of 1. Alright, so that will be one of the approaches, is just try to rewrite all the occurrences of s by some consistent shifted version of s. A tool that will come in handy for doing this is completing the square. So for example, let's say what we had was something like s squared plus 4s plus 8. We can find the square that starts off this way. So this is the same as s squared plus 4s plus 4 plus 4, which is s plus 2 squared plus 4. And if you need extra practice on this, the phrase is completing the square, and it's a thing that has occasionally danced across the curriculum of different algebra classes you might have been in, and it's also something that is done often in integration. So as an example here, let's say what we had was f of s equals s minus 3 divided by s squared plus 4s plus 8. So the reason why we would we would want to complete the square here is to rewrite this as this form. So then this matches the general format of a trigonometric function. So then basically we want this to be all in terms of an s plus 2 minus 2 minus 3 And so that's going to equal s plus 2 minus 5 over s plus 2 squared plus 4. And so then this we could break up into s plus 2 over s plus 2 squared plus 4 minus 5 over s plus 2 squared plus 4. And then this then becomes a shifted cosine, and since k here is going to be equal to 2, so shifted cosine 2t, and here this is going to be a shifted sine 2t. So what that means is then f of t is going to be equal to, well, we have a equals negative 2, and we have a equals negative 2 there. So we're going to have e to the negative 2t cosine 2t minus 5, and then ordinarily sine would involve having a copy of k in the numerator, so it's going to be 5 halves, and it's shifted, so it's going to be e to the minus 2t sine 2t. So this is the shift, and that's the k. And then the other option that is in front of us is to just use partial fractions. When the quadratic can be factored, we'll usually use partial fractions. And an example of something like this would be something along these lines. Let's say what we had was this is going to be f of s equals s divided by s squared minus 3s minus 10. Well, that can be factored into an s times s minus 5 and an s plus 2. So then, if we want, we can break this into the two terms that the technique of partial fractions will lead us to get. So this is going to equal some mystery a over s minus 5 plus a mystery b over s plus 2. Which means then that s is equal to, on the one hand, a times s plus 2 and b times s minus 5. And then we can just do the typical things to find the a and b, set s equal to negative 2 to cancel out the a's. So then negative 2 is equal to nothing, b negative 7, which means if we divide, that b is going to equal 2 sevenths. And if s equals 5, Then we'll get 5 is equal to a times 7, which means that a is going to equal 5/7. And so then we'll have that f of s is equal to 5/7 times 1 over s minus 5 plus 2/7 times 1 over s plus 2. Now technically we could actually think of each of these as being a shift, but these actually are each easy members of our catalog. And so that means then f of t is equal to 5/7 e to the 5t plus 2/7 e to the minus 2t. So the main innovation in this section was just finding a way to re-express complicated expressions such as we saw in the previous examples as entirely involving a shifted function of s. So s minus 2, s plus 2, something like that. Now note, the examples we just did could all have been done by some other method, and that will generally be the case. So many inverse Laplace transforms can be done by several possible methods. And if you do choose a different method, your answer may appear to be different, but it should end up being actually the same. So this will produce different seeming functions but which are equivalent, at least for t greater than or equal to 0. So it'll produce different seeming functions, but those different seeming functions will all be equivalent for t greater than or equal to 0. So that's section 7.3. Now in section 7.4, what we are going to do is approach some of these very same problems by some other means. Again, we're going to be developing lots of different ways of skinning these cats. So 7.4 has to do with derivatives, integrals, and products of transformations. So the idea here is that we will have several tools that we will use to arrive at alternate means of either finding the Laplace transform or the inverse Laplace transform of various functions. So the idea here is there are other ways to get either the Laplace transform or its inverse based on known functions. And in most of these cases, what we will be giving is an alternative to some other method that we know that might turn out to be more convenient. So first off, let's now define what is called a convolution of functions. So the convolution of functions is a third function that's produced out of two, and we would write it like this. So f asterisk g represents the function generated by the integral. It's going to be the integral from 0 to t so f convoluted with t, or with g of t, is going to be the interval from 0 to t of f of tau times g of t minus tau, and it's a derivative with respect to tau. Now the reason for bringing this up is the following, and there's what's called the convolution theorem. And what the convolution theorem basically tells us is this. So the Laplace transform of f star g which is a function of t, is the same as the Laplace transform of f times the Laplace transform of g. In other words, f of s times g of s. And that's nice, but what's more useful is the inverse of this, which is to say, and the inverse Laplace transform of a product of two pieces, each of which we know, is equal to the convolution of those two functions inverse Laplace transforms. So to use this, typically we'll be looking at the second direction of this, and the way we'll typically be using it is to find a way of breaking down the expression that we see into two pieces, each of whose inverse Laplace transforms we know. So break down the expression into factors whose inverse Laplace transform is known. Or transforms are known. And this is often an alternative to integrating by partial fractions, to using the technique of partial fractions. So this often replaces partial fractions. Replaces, for example, partial fractions. Now an example of something like this might be, suppose we wanted to find the regular function whose Laplace transform was this. So if f of s is equal to, let's say, 1 over s squared times s squared minus 1. So here, actually make it s squared plus 1. So here, what we would be talking about is the function that is the product of 1 over s squared and 1 over s squared plus 1. And each of these we can then take piece by piece. So what this means is that we'll be dealing with two little functions. We could say a of t is equal to just t. And here, b of t, according to the table of Laplace transforms, is equal to the cosine of t. And so what we'd be dealing with here is f of t is equal to the convolution of a and b of t, which would be the integral from 0 to t of, on the one hand, just tau, times, on the other hand, cosine of t minus tau. D tau. Now here, when it comes to this, we can use the technique of integration by parts, and u would equal just tau, meaning that du would equal d tau, and then over here we could have dv is equal to cosine t minus tau d tau, meaning that v is equal to, now here what we have is tau being a variable, t being considered to be just a constant, and so what we will have is negative, and then it's the invert, so the antiderivative of cosine is sine, and it's going to be t minus tau. And then what that's going to give us is the integral from 0 to t of u times v, so that's going to be tau times negative sine t minus tau. That's going to be going from 0 to t minus the integral from 0 to t of v du, so it's going to be negative sine t minus tau d tau. Now here we're going to be plugging in tau equals t and tau equals 0. Now if tau equals t, we're going to be getting 0 here, and the sine of 0 is 0, so it's going to be 0. And if tau equals 0, then we're going to be getting another 0 on that side. And so then over here, what we'll be getting is, so the antiderivative of sine is negative cosine. So here, those two negatives might cancel each other out. And then we'll have minus, but then there's another negative yet further in there. So negative, 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 4 negatives to make a positive cosine t minus tau. And that's going to be plugging in at 0 and t, which is going to equal 0 plus, now here, plugging in a t, that's going to be a 1, because that's going to be, so if tau equals t, then that's going to equal cosine of 0. Actually, here, let's just go one step at a time. Cosine of t minus t minus cosine of t minus 0. And that's just going to equal 1 minus cosine of t. So that's what we would get if we did this by the method of convolution. We could have also used the method of partial fractions, or we could have used the method of anti-differentiating. So we saw how to do problems like this where there were extra factors of s squared by just doing repeated anti-differentiation of the function that we already knew this was going to equal. And in particular, here we would be anti-differentiating cosine twice. But this is another way. Now here are some more useful formulas. These are all twists on the same theme. And they all come along these same lines. So if f of s is equal to the Laplace transform of f of t, so capital F of s, Laplace transform of little f of t, then first off, the Laplace transform of negative t f of t will be equal to the derivative of f of s. Then, by switching the place of the negative here, we can then rewrite this as Laplace transform of t f of t, t f of t will be negative derivative of f of s. And then by the same token, we can move the Laplace transform over, and we can say that t f of t would be the inverse Laplace transform of negative f prime of s, and it's the derivative with respect to s in that case. And then that means that and we can pull the negative out, and we can say that f of t is going to equal negative 1 over t inverse Laplace transform of f prime of s. So these all are clearly in flow with each other. And then as far as the integral formula, we can also, if we have something like this, so this is actually a twist on a formula we already had. So we have the Laplace transform of f of t over t. This is the same as the integral from s to infinity of f of sigma d sigma. Now we can use these as follows. So one way of using them would be an example like this. Let's say we want to find Laplace transform of, let's just say, t cosine 3t. So t cosine 3t. Well, if that's what we want, then we can just identify what's going to be playing the role of f here. So f of t is going to equal, cosine 3t, which means that f of s is going to equal, so this is the cosine, so that means it's going to be s over s squared plus k squared, which is 9, according to our table of Laplace transforms. And then what that means is this is going to be equal to negative f prime of s. So that means f prime of s, we would take the derivative of this, and we can use the quotient rule here, or we can rewrite it as a product. And in either case, if we want to take the quotient of this, it might be helpful to rewrite this as s times s squared plus 9 to the negative 1. So this is equal to, now take the derivative, that's going to be just s squared plus 9 to the negative 1, and then the s, and then leaves that one alone, so minus s squared plus 9 to the negative 2. And then that's going to equal 1 over s squared plus 9 minus s over s squared plus 9 squared, which is then just going to equal, if we find a common denominator, we'll multiply the top and bottom of this by s squared plus 9, and that's going to be s squared plus 9 minus s divided by s squared plus 9 squared. So there's that. But then what that means is this is going to equal the opposite of that. So negative s squared minus s plus 9 divided by s squared plus 9 squared. So that's one way of using this, is if you have one that you already know, you can take the derivative of that, and then we can take the opposite of that in order to get the Laplace transform. Let's say, on the other hand, we had something where we had a fraction. For example, let's say we were interested in the Laplace transform of, say, sinh t divided by t, so the hyperbolic sine of t divided by t. Alright, so here we would be using the Laplace transform of f of t over t formula, And in this case, the f of t is going to be equal to the sinh of t, which means then that the Laplace transform f of s is going to be, now the formula for the sinh t off the table is similar to the sign. The difference is that what we have is a minus in the bottom instead of a plus. It's the main difference between the hyperbolic and the trigonometric functions. In particular, it's going to be kt, so it's going to be k over s squared minus k squared, which, for the record, is, well, we'll cross that bridge when we come to it. So now then, we would be interested in finding the integral of this as s goes from 0 to infinity. So then what that means is the Laplace transform of sinh t divided by t is going to equal the integral from s to infinity of f of s, which is going to be 1 over sigma squared minus 1 times d sigma. Now here we are going to need to deal with this in one way or another, and in particular partial fractions would be the most common method employed here. So 1 over sigma squared minus 1 is the same as 1 over sigma plus 1 times sigma minus 1, which we can, by partial fractions, assume is equal to a over sigma plus 1 plus b over sigma minus 1. So then what that would mean is that if we multiply both sides of this by the common denominator of sigma plus 1 sigma minus 1, we're going to have 1 equals a times sigma minus 1 plus b times sigma plus 1. And from this equation now, setting sigma equal to 1 is going to give us 1 equals, and that's going to cancel that out, and it's just going to give us a b times 2. So that means b is going to equal 1/2. Alternatively, if sigma equals negative 1, that's going to give us now 1 equals a times negative 2, which means a is going to equal negative 1/2. Which means that 1 over sigma squared minus 1 is the same as negative 1/2 1 over sigma plus 1 plus 1/2 1 over sigma minus 1, which then in this case means that we could pull out the 1/2 and rearrange it slightly to make it 1/2 1 over sigma minus 1 minus 1 over sigma plus 1. This will make the integral a little bit easier. So then what this means is that the Laplace transform of sinh t over t is going to equal the integral from s to infinity of 1/2 1 over sigma minus 1 minus 1 over sigma plus 1 d sigma, which is going to be 1/2, and then here what we're going to have is the natural log of sigma minus 1 minus the natural log of sigma plus 1 s to infinity, and so then that's going to equal 1/2, and by the properties of logarithms that's going to be the natural log of sigma minus 1 over sigma plus 1 from s to infinity. But But the natural log of sigma minus 1 over sigma plus 1 will go to 1 as this goes to infinity. Note. The limit as sigma goes to infinity of ln sigma minus 1 over sigma plus 1 is equal to ln of 1, which equals 0. Because the leading terms of this are 1 sigma and 1 sigma, so you multiply the top and bottom of this each by 1 over sigma, for example. That'll be 1 minus 1 over sigma plus 1, or over 1 plus 1 over sigma. Sigma will go to infinity, and so that will just end up with a 1. So then this is equal to, in this case, 1/2 now. And we've got 0 minus ln s minus 1 over s plus 1. But we could, if we wanted, bring the negative in, and then that would make it the reciprocal. So it'd be 1/2 ln s plus 1 over s minus 1. So that would be how this could go. And now one more example along these lines. We could have, let's take C, the Laplace transform of e to the t minus 1 divided by t. So here, once again, we have a fraction, and so it is a t on the bottom, so we need to identify what the function on the top is, what its Laplace transform is, and what the integral of that would be. So f of t here would be e to the t minus 1, which means that the Laplace transform here is going to be, off the table, e to the 1t, so this means it's going to be 1 over s minus 1, minus 1, so that's going to be just 1 over s. The Laplace transform of a constant is 1 over s times whatever the constant is. So then we are interested in the Laplace transform of e to the t minus 1 divided by t, which equals the integral from s to infinity of this, but with sigmas in place of s's. So 1 over sigma minus 1 minus 1 over sigma, the integral of that with respect to sigma, so d sigma. So this is going to be equal to the natural log of sigma minus 1 minus the natural log of sigma. And we're going to be plugging in s and infinity. So this actually, by the same properties of logarithms, is going to be the same as the natural log of sigma minus 1 over sigma s to infinity, but then this is actually the same, we can distribute that sigma, as the natural log of 1 minus 1 over sigma s to infinity. And if we plug in infinity here, this will become 0. 1 minus 0 is 0. The natural log of that is equal to, 1 minus 0 is 1. Natural log of 1 is natural log of 1 is equal to 0. And so we would get negative ln 1 minus 1 over s. We could rewrite this again in a similar way to the way we rewrote the other one, although there's not much value to that. One note that is kind of a technicality, but important to have in the record. So note the formula, the Laplace transform of f of t over t equals the integral from s to infinity of f sigma d sigma. So this requires that the limit as t approaches 0 from a positive direction of f of t over t exists and is finite. So it requires that the limit as t approaches 0 from a positive direction of f of t over t exists and is finite, and this happens to be true in all of the above cases. This is true by L'Hopital's rule. In each of the above cases. So you're not going to be given one where this isn't satisfied. It's just in the record that this has to be true in order for this to be valid. But it won't ever come back to bite you should you neglect it. Now let's change gears a little bit and talk about something else that is another aspect of Laplace transforms, and it has to do with periodic and piecewise continuous input functions, and that's the title of section 7.5. Periodic and piecewise continuous input functions. And here's the basic idea. To start with anyway, before getting to the periodic part, the idea is we can, quote, delay a function by using the unit step function. Which we'll call u of t, and here's how. So if we have a function, let's say f of t is just going up like this, and we want the whole thing to be delayed until a t value of a, but then to just go about its business as usual, what this would be is u of t minus a times f of t minus a. Or in other words, u sub a of t times f of t minus a. Now that's all well and good. We can delay the onset of a function, but we can also actually turn it back off and only get a section of the function. So we can turn off a function by subtracting another piecewise, or I should say another unit step function. So, for example, if our f of t was again that little line going up, and I wanted it to go specifically from a starting value of a to an ending value of b, and I just wanted it to be completely shut off right there. Start there, end there. Then what I could do is I could do u of t minus a minus u of t minus b all times f of t minus a. In other words, u sub a of t minus u sub b of t f t minus a. Now the reason for wanting to do this is the following. Then we can create a more complicated piecewise function out of simple parts. So for example, and this is an example that was from 7.1. Let's say that the function that we had was something like this. So it was going up until the point from 0, 0 to 2, 2. Then it was going horizontally till it reached 4, 2, and then it started coming down, and it came down at 5. So let's call this 3 parts. So let's say a of t is equal to just t, and that's the first part. B of t is equal to 2, that's the second part. And c of t is equal to 2 minus 2t. That's that last part. But each shifted. So this one would have been just going like that, but we shifted it over. This one would be going like that, but we shifted it over. This one we didn't need to shift because it was already doing what it was supposed to be doing. Then f of t is going to equal, well, it starts at 0 and goes till 2. So that means we're going to have u of t minus u2 of t times just t. And then the next section of it, so then it turns off, and then the next section of it goes from u2 of t to u4 of t, and that's just equal to 2. And then plus, then the last part here is going to be from u4 of t to u5 of t. And that's just going to be times now c of t minus 4. So this part is a of t minus 0, what's going on there. This part is b of t minus 2, so what's going on right there. And then this part is c of t minus 4. But then we can simplify that a little bit, and so we should. So what we will do, move that a little bit more in view here. What we will do is just now distribute the terms. However, we will do so somewhat idiosyncratically. So what we're going to have here is u of t times t minus u2 of t times t plus, distributing the 2 now, 2 u2 of t minus 2 u2 of t, sorry, u4 of t, u4 of t, and then how we're going to do this next part is we're going to just do plus u4 of t times 2 minus 2 times t minus 4. I'm not going to do anything more with that part. Minus u5 times 2 minus 2 times t minus 4. Now here's the reason for doing this. The reason why we want to break this into these little parts is that there is a way of figuring out the Laplace transform of each of these little parts. And in particular, Laplace transform of ua of t times f of t minus a. This actually is just equal to e to the minus as f of s. And then the Laplace inverse of of e to the minus as, capital F of s, is equal to u sub a of t times f of t minus a. Now applying this to the example, let's start with a simpler example. The example will be something like this. Let's say we have a function from 2 to 3 that just goes up like that from 0 to 1. And we'll call that f of t, and the goal will be find capital F of s. Alright, well, let's think about f of t. So f of t appears to be a shifted version of the function that is just t. So if we say that g of t is just equal to t, so it goes like that, then f of t would be g of t shifted over by 2. So it's going to be u2 of t, but then it gets turned off by the time it gets to 3, so that means minus u3 of t times g of t minus 2. So here, what that's going to mean is u2 of t minus u3 of t times just t minus 2, which is going to equal u2 of t times t minus 2 minus u3 of t times t minus 2, which this part is actually in good shape for this formula up here. However, this part is not. So what we'll do is we'll rewrite it as u2 of t minus 2. We need that number and that number to match. So the way we do that is we just do a little manipulation here. u3 of t times t minus 3 plus 1. So then here what we would have is equal to, then if we want to take the Laplace transform of this, so then the Laplace transform of f of t would equal the Laplace transform of u2t times t minus 2, which fits the form, minus Laplace transform of u3t times t minus 3 plus 1, which now also fits the form. You should never see a naked t, you should only see a t minus 3 if it's times u minus 3. And so then this is going to equal e to the minus 2. So then here we should think of this as t, and here we should think of this as t plus 1, each shifted. So it's shifted t and a shifted t plus 1. It's going to be e to the minus 2s times the Laplace transform of t minus, just t, which is going to be 1 over s squared. Minus here, we're going to have e to the minus 3s times the Laplace transform of t plus 1, which is going to be 1 over s squared plus 1 over s, which is going to then just equal e to the minus 2s over s squared minus e to the minus 3s over s squared minus e to the minus 3s over just s. Now back to the example that we had. So in the first example, what we had was, again, remember, f of t equals u of t times t minus u2 of t times, we want this to be t minus 2, so we have to do t minus 2 plus 2, plus 2 u2 of t minus 2 u4 of t plus u4 of t times 2 minus 2 times t minus 4 minus u5 of t times 2 minus 2 times t minus 5 plus 1 and just this part now we can rewrite u5 of t times 2 minus 2t 2t minus 5 minus 2, so that's going to be that's then going to be u5 of t times 2 minus 2, so it's going to be negative 2 t minus 5. So then what we will have in this is going to be a collection of shifted functions. So then that means that f(s) is going to be Laplace transform of u of t times t minus the Laplace transform of u2 of t times t minus 2 plus 2. Again, we always need this part to only include a mention of t minus 2, never a naked t, plus the Laplace transform of u2, 2u2t minus Laplace transform of 2u4 of t plus the Laplace transform of u4 of t times 2 minus 2 times t minus 4 minus the Laplace transform of u5 of t times minus 2 times t minus 5. And then here, the shifted functions that we're talking about are t shifted by 0, t plus 2, not relevant, 2 minus 2t, and then minus 2t. And so what we'll have right here is just actually going to be e to the 0, e to the negative 0 s, so that's just going to be 1 times 1 over s, 1 over s squared I should say, which is the Laplace transform of just a t. Here it's going to be minus e to the minus 2s times, and what we're going to have here is going to be t plus 2. So it's going to be 1 over s squared plus 2 over s plus. Now here, what we have is basically a constant function being shifted. You could think of it, or we actually already had the mechanisms for dealing with this. But in any case, it's going to be e to the minus 2s times 2 over s, and then minus, we're going to have e to the minus 4s times 2 over s, And then plus on the next one down here, we're going to have e to the minus 4s times 2 is going to be 2 over s minus 2t, 2 over s squared. And then the last one here is going to be minus e to the minus 5t, or minus 5s, I mean. And then that's going to be minus 2t, so it's going to be minus 2 over s squared. Now, if we look over the terms here that are in play, we are going to get a lot of cancellation, namely, here, let's not be heroes, minus e to the negative 2s over s squared minus 2e to the minus 2s over s plus e to the minus 2s, I guess plus 2 that over s, minus 2e to the minus 4s over s plus 2e to the minus 4s over s minus 2e to the minus 4s over s squared plus 2e to the minus 5s over s squared. So now, like terms can be cancelled, and in particular, you'll notice that this one and this one cancel each other, as do this one and this one. And I think that's it. So then what we're going to end up with is 1 over s squared minus e to the minus 2s over s squared minus e to the minus 2e to the minus 4s over s squared plus 2e to the minus 5s over s squared. Now this looks like a lot of work, but I will remind you how much work it took us the last time we did this very problem, back in section 7.1, and in particular, if you'll recall, what we did was we had to set up these integrals, do the integrations by parts, and then put all the pieces together. And then when we did put all the pieces together, you'll notice that what we got was, in fact, actually the equivalent of this. So we rearranged it a little bit differently, but it was the same. So this example was a little bit, so it is slightly shorter doing it this way, although still rather difficult. The key to all of this is you have to rearrange the expression so that you only have a function of t minus a over here. So, note, always arrange the function so that when you have the Laplace transform u sub a of t times something, this something is always an explicit function of t minus a. So this only involves t minus a, not just a bare t. Now we get a special case of the shifting that you get by using the unit step function in the case of periodic functions. So first off, the definition of a periodic function is so a function f is periodic with period p if f of t plus p equals f of t for all t. This means that we can think of f as being an infinite sum of translated copies of its first period. So thus, if we write f tilde to mean the function f restricted to its first period, is the function we'll say to the interval 0 to p. In other words, the first period. Then f of t is equal to the sum from I equals 0 to infinity of u of t minus ip times f tilde of t minus ip and this is for t greater than or equal to 0. For all Laplace transforms, we are only ever really interested in t being greater than or equal to 0, because that's where the interval that is in question is in effect. But then we can find the Laplace transform of both sides, and because it's a linear transformation, that means we can distribute it over the sum. And so then this is going to be the sum from I equals 0 to infinity. But as we've already found, this is equal to the sum I equals 0 to infinity e to the negative, and it'd be a here, so it's going to be IP S times the Laplace transform of f tilde of t. But this part, since it's always the same, we can pull it out to the front. It's shared by all these vectors. And so we have now this expression, the Laplace transform of the truncated version of f times this sum over here. And this part right here is then going to be the integral from just 0 to p of e to the minus st f of t dt. So it's just cut off at the end of the first period, times here this, which is a geometric series. So this is a geometric series of the form, so in other words, being geometric means we have sum from 0 to infinity of r to the I, which equals then 1 over 1 minus r. So then what that means is, so thus, the Laplace transform of s is equal to the integral from 0 to p e to the minus st f of t dt times 1 over 1 minus, and here it's negative ps that's playing the role of the r, so it's e to the negative ps. So, and this is usually written the other way just for clarity. E to the negative ps times the integral from 0 to p e to the minus st f of t dt. Okay. So that now is something that we will be able to use in different contexts whenever we have a periodic function and we are taking the Laplace transform. An example of this might be what is called the square wave function. And the way this looks is that it is a function that alternates between being constant at 1 and at negative 1. And we'll say that it is closed on the right, closed on the left, open on the right, just to avoid not being well defined. Dot, dot, dot. And in particular, we'll say that these points are coming at A, 2A, 3A, and so on. So then this is periodic. Call this f of t. So this is periodic with period. At first you might say A, but actually 2A, because that's when it fully repeats its entire cycle. Which then means that, And here, the truncated version of the function is just going to be equal to the piecewise function, that is 1 if 0 is less than or equal to t, which in turn is less than a, and negative 1 if a is less than or equal to t, which is less than 2a. Alright, so then f of s would be 1 over 1 minus e to the negative 2as times, and now here we'll have the two pieces of the integral here. We're going to have the first 0 to a installment, and that's going to be times just, it's going to be the integral of e to the negative st times just 1 dt, and then plus the integral from a to 2a e to the minus st times negative 1 dt. So then what we're going to have here is going to be 1 over 1 minus e to the minus 2as times, and then right here, this integral is easy enough to do, negative 1 over s times e to the minus st evaluated at 0 and at a. And then this is going to be the same thing, minus 1 over s, except it's going to be, the difference is that the negative will get canceled by that. And then it's going to be e to the negative st from the interval a to 2a. And so then when we actually plug in these endpoints, then what we're going to end up with is going to be negative e to the minus sa over s minus negative, and it's going to be putting in a 0 for the t, so it's going to make it a 1 over s, and then plus over here we're going to have e to the minus 2 as divided by s, and then we're going to have plus, and then that's going to be making a e to the minus as over s, which is going to then cancel this part over here. Pardon me, not cancel that, because that's a minus. That's to be subtracted. So then these are like terms. And so what we're going to have is 1 over 1 minus e to the minus 2as. And then in here, what we're going to have is going to be, and we can pull out, let's pull it out later. We can pull out an s when we think the time is right. So here we have 1 over s plus e to the minus 2as over s minus 2 e to the minus as over s. So we can pull out the s, the 1 over s, and that's going to make 1 over s times 1 minus e to the minus 2as, and then, times here, and then that's going to make a 1 minus e to the minus as plus e to the minus 2as, but since this is actually the square of that, but e to the minus 2as equals e to the minus as all squared, So this is going to be 1 over s times 1 minus e to the minus 2as times 1, sorry, there's a minus a 2 there. So 2, there's a 2 in there. So minus 2e to the minus as plus e to the minus as squared, which is actually then the recipe for a perfect square trinomial, as it's called. So then, how this is going to shake out is it's going to be a 1 over an s times a 1 minus e to the minus 2as times 1 minus e to the minus as all squared. But thinking about this, that is, as we just said, the same thing as the square of e to the minus as. And so what we have is 1 minus e to the minus as all squared divided by s times 1 minus e to the minus as squared, which is going to then be 1 minus e to the minus as squared divided by s times 1 minus e to the minus as times 1 plus e to the minus as. It's a difference of squares. Which then means we can cancel a little bit, and we have 1 minus e to the minus as divided by s times 1 plus e to the minus as, which, depending on how you have seen it or not, this may or may not be familiar to you, but this is actually a known function, the part besides the s here. And in particular, if you've never seen how this works before, what we can do is we can just multiply both sides, or both the top and the bottom, by 1/2 e to the as over 2 . And when we do that, we're going to have 1 over s times, and I'll just separate that up. We're going to have 1/2 e to the as over 2 minus e to the minus as over 2, because when we combine those, we'll just add the exponents, divided by, and 1/2, and divided by 1/2 e to the as over 2 plus 1/2 e to the minus as over 2, which then is going to be 1 over s times the hyperbolic sine of as over 2 divided by the hyperbolic cosine of as over 2. And so then that's going to mean we're going to have 1 over s times the hyperbolic tangent, or tanh, as it's sometimes pronounced. Sometimes also pronounced tangent, but that's not so common. Not as common in the United States anyway. More common, I think, in Britain. Alright, and there is the Laplace transform of the square wave function. So it's 1 over s times the tanh of as over 2. We'll see how to use this later. We're going to make use of this in a study both of the mass dashpot and spring situation, And then also we're going to look at it in the context of circuits, but that will be for a later section. All right, so there was one example. Now let's do another example of a similar variety. And in particular, let's try an example such as this. So let's say that we wanted to find the Laplace transform of a periodic function that went like this. So now it's not going to be square, it's going to be what's called a triangle wave. And in particular, we'll go with up, down, up, down, up, down. We'll go with that whole motif throughout the rest of time. And let's say that the amplitude here is 1. And let's say that this also is 1. And it just keeps going. Okay, so this is going to be our function. Well, first off, the period here is 2. And one whole period, sorry, the period here is 1, I should say. Period is 1. And one whole period means 2 sections, an up stroke and a down stroke. So f tilde of t, so it's going to be the f restricted to the first period, is going to be, looks like it's just t as 0 is less than or equal to t is less than 1/2. Less than or less than or equal to, really doesn't matter. And then for the next one, so it looks like, oh, sorry, it should be 2t because it's going up 2, it's going up 1 as it goes over 1/2. So the slope is going to be 2. And then here, if we look at the downstroke, it's going to be, well, it would have been up at 2 if it had been allowed to continue that. So then that's going to be negative 2t plus 2, and that's if 1/2 is less than or equal to t is less than or equal to 1. And it doesn't matter so much whether you which endpoints you include. Just try not to violate the well-definedness of your function. And then a quick check on this: is this right? If we plug in 1/2, we should get 1. So we would get -1 plus 2 is 1. And if we plug in 1, we should get 0. Okay, so it checks out. So that's the upstroke, that's the downstroke, and then that means that f of s is going to equal 1 over 1 minus e to the negative s, so the period is 1, times the integral from 0 to 1/2 of 2t, or negative st times 2t dt. And then we're going to have plus the integral from 1/2 to 1 e to the negative st times negative 2t plus 2. Okay. Now, in evaluating this, what we can do is we can now just game out some integrations by parts. You can break this into 2 pieces if you want, or you can leave it in the form that it currently is. Doesn't really make a huge difference. I'm going to use it in the form that it currently is. So I'm going to say then for this one, u is equal to 2t, du then will be 2 dt. For this one, I will say, here I'll say dv is equal to e to the minus st dt. V then will be negative 1 over s e to the minus st. For this other one, I'm going to have my u be the negative 2t plus 2. And I'll have my du correspondingly be negative 2 dt. My dv will be the same as before, e to the minus st dt. And my v then correspondingly will be negative 1 over s e to the minus st. Now we're just going to take this in two pieces. So I will just say I1 is equal to the integral, and I won't even worry about the bounds until later, negative st times 2t dt. And I'll say that I2 is equal to the integral e to the negative st to negative 2t plus 2 dt. Okay. So now, actually, so I need to keep my eyes on the u's and v's here. So now this is going to be equal to uv, so it's going to be negative 2t over s e to the minus st minus the integral v du. You can pull out the negative and make it integral. You can pull out the constants, which are going to be a 2 and an s. That's from the perspective of t anyway. Minus st dt, which is going to be negative 2t over s e to the negative st. This is going to be minus because I'm going to pull out negative 1 over s, so it's going to be 2 over s squared e to the negative st. Okay. On this side, we are going to have a very similar shakedown, or shakeout. So uv, so it's going to be negative, I'll just distribute the negatives, so it'll be 2t minus 2 over s times e to the negative st. And then for the integral of v du, I am going to have negative, 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 so that makes negative. I'm going to pull out the 2 over s, and it's going to be the integral e to the minus st dt. And so then this is going to be 2t minus 2 over s e to the minus st minus, but now it's going to become a plus 2 over s squared e to the minus st. Okay, so then that means that I1 from 0 to 1/2 is going to be equal to, well, let's see, I plug in 1/2, and it's going to be negative 1 over s, negative 1 over s e to the minus s over 2 minus 2 over s squared times e to the minus s over 2. Then I can plug in t equals 0, and that's going to be minus 0. That'll all just be 0. And then minus 2 over s squared and times e to the 0. So that's going to be now negative 1 over s e to the minus s over 2 minus 2 over s squared e to the minus s over 2 plus 2 over s squared. So there's that. Now for I2, from the bounds of 1/2 to 1, that's going to now be, so it's going to be 2t minus 2. If I plug in 1, that's going to be 0, plus 2 over s squared, and I plug in 1, so it's going to be e to the minus s. Minus, now I plug in 1/2, and that's going to make 1 minus 2, it's going to make a minus 1. Minus 1 over s, e to the minus s over 2. And then the next one is going to be plus 2 over s squared, e to the minus s over 2. Put the pieces together, it's going to be 2 over s squared, e to the minus s, plus 1 over s, e to the minus s over 2, minus 2 over s squared, e to the minus s over 2. And now, then, if we were to put the pieces together to get the capital F of s, so the Laplace transform of the function, what we'll have is 1 over 1 minus e to the minus s times negative 1 over s e to the minus s over 2 minus 2 over s squared e to the minus s over 2 plus 2 over s squared plus 2 over s squared e to the minus s plus 1 over s e to the minus s over 2 minus 2 over s squared e to the minus s over 2. Now some things here will combine, some things will cancel. Those will cancel each other. These two will combine with each other, and so then we'll have 1 over 1 minus e to the minus s times, now we'll have minus 4 over s squared e to the minus s over 2 plus 2 over s squared plus 2 over s squared e to the minus s. And then, so those s terms are just canceled, so we can actually pull out a common factor of 2 and a common factor of s squared. So it's going to be 2, I'll pull out here s squared, we'll put down here 1 minus e to the negative s, and then here what will be left behind, I'm going to reorder it now as e to the minus s minus 2 e to the minus s over 2, and then plus 1. But if we actually look at this, this is actually something that we could combine a little bit more, because e to the minus s is equal to e to the minus s over 2 squared. So therefore, this is actually a perfect square. So that means we're going to have 2 over s squared times 1 minus e to the minus s times e to the negative s over 2 minus 1 squared. So then I could put this a little bit more succinctly as 2 times e to the minus s over 2 minus 1 squared over s squared 1 minus e to the minus s. But again, because of this fact, this is actually equal to 2. And the square, by the way, means that that the order of these can be reversed, because it would not be because it would be just multiplying each by -1. So we can reverse the order of these. So 1 minus e to the minus s over 2 squared, because inside a square it becomes always the same if it was negative negative. Okay, and then that's s squared times 1 minus e to the negative s over 2 squared, which is going to be 1 minus e to the negative s over 2 squared divided by s squared times 1 minus e to the negative s over 2 times 1 plus e to the negative s over 2. And so what that is going to do is going to produce the same sort of cancellation that we saw previously. And so we're going to have 2 times 1 minus e to the negative s over 2 divided by s squared times 1 plus e to the negative s over 2. And then if we want, we can actually do the same operation that we did previously to rewrite this. So the way that would go is we could then take the 2 times 1 minus e to the minus s over 2 divided by s squared times 1 plus e to the minus s over 2. And what we would do is we would multiply the entire top by 1/2 e to the negative, not negative, just s, divided by 4. And the bottom also by 1/2 times e to the s over 4. And the reason for that would be, then when we distributed that through, what we would end up getting on that part and that part would be 2 times 1/2 e to the s over 4 minus 1/2 e to the negative s over 4. Down here we'll have s squared, we'll have 1/2 e to the s over 4 minus 1/2, plus 1/2 e to the negative s over 4. And the reason for doing that is the same as what it was before. That makes it 2 times the hyperbolic sine, so 2 times sinh of s over 4 divided by s squared times cosh of s over 4. But then we could rewrite that to be 2 over s squared and the hyperbolic tangent of s over 4. Now, that bears a shocking resemblance to the result we got earlier for the square wave. Coincidence? No. And here's the connection. Notice something. So if you were to take the derivative of our function, let's just call this a note. So note, the derivative of our function. So if you look back at what the graph of our function actually was, the derivative of our function is going to be constantly equal to here 2, because it goes over 1/2 of 1, here negative 2, here positive 2, here negative 2. So it's going to be 2 times the square wave function with a equals 1/2. So if g of t is equal to, or let's say, if g of t is square wave function, just to keep us from having to write this function, sometimes it's abbreviated SW, but with a equals 1/2, then f of t is equal to the integral from 0 to t of 2 times g of tau d tau. Then, by the formula from section 7.2, fs is going to equal 2 times g of s divided by s, which is going to equal 2 times the hyperbolic tangent, 2 times the hyperbolic tangent, and as we discovered, it's a times s over 2, so that's going to be 1/2 times s divided by 2, all divided by s. Sorry, this was already divided by s, so this is going to be divided by s again. So that's going to be 2 over s squared, hyperbolic tangent of s over 4. So we can actually, by cleverness, if we notice something convenient, like the fact that our function is the antiderivative of a known function, then we can actually get a shorter, slicker way to the finish line. But either way works. We got there all the same. So that'll have to do it for now. It's been a long lesson. So join me next time for another episode of Math 256. In the meantime, remember, there's not going to be a lecture on the 25th of May because of Memorial Day, and also the exam is May 27th, so there won't be a lecture then either. So I'll be with you again in the month of June. Till then, bye.